You flip a light switch, the bulb glows. You flip it again, and the room goes dark. Simple causality. Cause, then effect, marching forward. Now picture this. You flip the switch, and in the instant the circuit closes, the bulb explodes. Not because the voltage is wrong or the filament is weak, but because the very act of completing the loop triggers a surge of energy from nowhere, a runaway feedback that destroys the device before it can finish turning on. That is not a faulty switch. That, according to some of the most careful calculations in theoretical physics, is what happens every time someone tries to build a machine that lets you travel backward through time. General relativity, Einstein's theory of gravity and space-time, permits roads back to yesterday. The equations say so plainly. Yet every attempt to engineer one on paper ends the same way. The machine annihilates itself at the moment of switch on, destroyed by a flood of energy that emerges from the vacuum itself. The obstacle is not technology. It may be a law of nature we are only beginning to see. Turn on the time machine, and the universe answers with a surge that tears it apart before the first second can loop back. The first person to notice that time travel might be written into the fabric of space-time was not a physicist dreaming of adventure. It was Kurt Gödel, the logician who had already shattered mathematics with his incompleteness theorems, and he noticed it while working out a birthday present. The year was 1949. Albert Einstein was turning 70, and his colleagues at the Institute for Advanced Study in Princeton each contributed something to mark the occasion. Gödel, by then Einstein's close walking companion, chose to solve Einstein's own equations, the field equations of general relativity, for a rotating cosmos. He expected, perhaps, a tidy cosmological model, one that respected the universal order of past flowing into future. What he found instead was a solution in which closed, timelike curves pass through every point. An observer in Gödel's cosmos could, in principle, travel along a perfectly ordinary path through space and arrive back at their own past. Not by moving faster than light, never that, but by following the curved fabric of space-time itself, which in Gödel's solution twisted into loops. Time, in his cosmos, was not a river with a single direction. It was a surface you could walk around. Gödel was obsessed with the nature of time, and this result carried a philosophical weight for him. If relativity allowed such a cosmos, what did that say about the objective reality of past and future? Einstein, when he understood what Gödel had done, was reportedly unsettled. Fortunately, our cosmos is expanding and does not rotate in the way Gödel's model requires, so we do not live inside a time loop. But the disturbing fact remained. General relativity itself, the theory that had predicted black holes and the bending of starlight and the expansion of the cosmos, did not forbid time travel to one's own past. The equations were silent on the matter. They permitted it. For decades, Gödel's cosmos sat as a curiosity, a mathematically beautiful oddity with no clear path to reality. Then, in 1974, a physicist named Frank Tipler found another way. He showed that an infinitely long cylinder of matter, spun fast enough, would drag spacetime around it so violently that light cones, the boundaries of what can influence what, would tilt over, allowing closed paths through time. The cylinder had to rotate at a significant fraction of the speed of light, and it had to be infinitely long, which is to say, an object that cannot exist. But the principle was clear. Rotation, frame dragging, and enough mass could, in theory, open a door to the past. The cosmos, it seemed, was charging an impossible price, infinity, for a time machine, but the equations still allowed the transaction. Why does this matter? Because by the 1980s, the question had moved from cosmology into something that looked almost like engineering. In 1985, the astronomer and novelist Carl Sagan was writing Contact, and he wanted a scientifically defensible way to send his protagonist across the galaxy. He called Kip Thorne, a physicist at Caltech and an expert in general relativity. Thorne and his students Michael Morris and Ulvi Yurtsever worked out a solution: a traversable wormhole, a tunnel through space-time with two mouths, one here and one there. The wormhole had to be threaded with exotic matter with negative energy density, violating what is called the weak energy condition, to hold it open, but the equations permitted it. Then they realized something unsettling. If you took one mouth of the wormhole and moved it, accelerated it to near the speed of light and brought it back, for instance, special relativity would cause time to pass more slowly for the moving mouth than for the stationary one. The two mouths would become desynchronized in time. Step through the stationary mouth into the moving one, and you step into the past. The wormhole, intended as a shortcut through space, turned into a time machine almost by accident. And this, Thorne later said, seemed to be the generic fate of any such structure. You did not have to try to build a time machine, you just had to build a traversable wormhole, and time travel came along for the ride. Here is the strange part. Thorne and his colleagues published their results, and the response from the physics community was not dismissal, it was concern. Because if you could really send something, even just a single photon, back through time, causality itself became fragile. You could imagine paradoxes, the classic grandfather scenario, where you prevent your own existence, or subtler contradictions involving information or energy. Some physicists, notably Igor Novikov, argued that paradoxes might resolve themselves through a principle of self-consistency. Only events that agree with their own past can occur, and the cosmos somehow enforces this. Others were less sanguine. The equations said time machines were possible. The intuition of nearly every physicist said they should not be. Someone needed to find the law that forbid them, or prove there was no such law. Stephen Hawking took up the question, and in 1992 he published a paper with a memorable title, Chronology Protection Conjecture. The abstract laid out the stakes plainly. Hawking proposed that the laws of physics do not allow the appearance of closed timelike curves, that beyond the permissive equations of general relativity, something deeper intervenes to prevent time machines from forming. He wrote, with characteristic wit, that there seems to be a chronology protection agency at work, keeping the cosmos safe for historians. But what could that agency be? Not a conscious enforcer, not a rule written into Einstein's equations, which, as Gödel had shown, were neutral on the matter. The answer, Hawking argued, lay in the quantum behavior of empty space. Think about the vacuum, the so-called emptiness between particles. It is not truly empty. Quantum field theory tells us that even in a perfect vacuum, fields are restless. Particle-antiparticle pairs flicker into existence and annihilate in spans of time so brief they borrow their energy from uncertainty itself. This is not speculation. The Casimir effect, measured in laboratories since 1948, proves it. Place two uncharged metal plates close together in a vacuum, and they attract, pushed together by the difference in vacuum fluctuations between the plates and the surrounding space. The vacuum has structure, and that structure carries energy. In flat, boring spacetime, these fluctuations average out. But near a forming time machine, spacetime is anything but boring. To understand what happens there, we need to talk about a particular kind of boundary, a chronology horizon. Imagine spacetime divided into two regions. In one, time behaves normally. Every event has a clear past and a clear future, and causes precede effects. In the other, closed time-like curves exist, and history loops back on itself. The boundary between these regions is the chronology horizon. It is the exact frontier where time travel becomes possible, the lip of the waterfall past which there is no return to normal causality. And at that boundary, something remarkable and violent happens. The first signal able to complete a time loop is a light ray, a closed null geodesic, in the language of general relativity. Physicists call it the fountain. Picture a ray of light circulating around this boundary, not quite completing a loop, then crossing the threshold where the loop closes. On its first lap, it carries whatever energy it started with. On its second lap, it meets itself, the same photon from the future, and the energies add. On its third lap, the sum adds again, and again. The energy grows not by addition, but geometrically. E becomes e to some power times e, then e squared times that, then e to the fourth. Within a time interval that, in principle, can be made arbitrarily short, the photon's energy diverges, becomes infinite. This is the runaway blue shift. Kip Thorne, in an interview years later, described it as being like the feedback between a microphone and its own speaker. Bring the mic close enough, and the faintest sound loops, amplifies, and screams to saturation in an instant. The photon, circulating at the chronology horizon, does the same. It does not stop at loud, it runs away. But light is not the only thing that loops. Quantum fields, the entities that underlie every particle and force, do as well. Those vacuum fluctuations, the particle pairs flickering in and out, now circulate around the fountain. Each virtual particle, as it completes a lap, gains energy from the geometry. The stress-energy tensor, the quantity that tells spacetime how much energy and momentum are present, begins to grow. Physicists compute this using a method called renormalization, a careful procedure for extracting finite, measurable predictions from the otherwise infinite mess of the quantum vacuum. In flat spacetime, the renormalized stress energy of the vacuum is zero, no net effect. But at the chronology horizon, the procedure yields something else. The tensor diverges. The vacuum, far from being passive, generates an infinite energy density at the boundary. And here is the thing about energy in general relativity. Energy tells spacetime how to curve, and spacetime tells energy how to move. This is the feedback loop at the heart of Einstein's theory. If the vacuum stress energy diverges, it feeds back into the geometry, into the curvature of spacetime itself. And that curvature, now wildly distorted, amplifies the vacuum fluctuations further. The machine, in trying to switch on, calls into being its own executioner. The chronology horizon, on the verge of forming, is ripped apart by the energy it summons from nothing. This, Hawking argued, is chronology protection. Not a prohibition written in advance, but a catastrophic instability that triggers the moment a time machine is about to work. Hawking was not the first to calculate this. In 1991, a year before Hawking's conjecture appeared in print, two physicists, Sung-Won Kim and Kip Thorne, had already worked through the numbers for a traversable wormhole on the verge of becoming a time machine. They found the same divergence in the vacuum polarization, the same runaway at the horizon. But they reached a different conclusion. Kim and Thorne argued that the divergence, while formally infinite in the equations, would be cut off by quantum gravity, the still unknown theory that governs spacetime at the smallest scales. And critically, they calculated that this cutoff would occur when an observer, approaching the chronology horizon, was still about 1 Planck length away. The Planck length is the shortest distance that has any meaning in physics, roughly 1.6 times 10 to the minus 35 meters, a billion times smaller than a proton, the scale at which spacetime itself is thought to dissolve into quantum foam. At that distance, Kim and Thorne found, the distortion to spacetime was absurdly small, about 1 part in 10 to the 35. A perturbation so tiny, they argued, could not possibly destroy anything. The time machine, they concluded, would survive. The closed timelike curves would form. Quantum gravity would cut off the divergence gently, long before it could do damage. Hawking disagreed. The entire debate, it turns out, hinged on a choice of measuring stick. Kim and Thorne measured how long it took an observer, in their own proper time, to reach the chronology horizon. In that frame, the last Planck length took a normal, finite amount of time to cross, and the distortion at that moment was negligible. But Hawking pointed out that proper time is not the only relevant measure. There is another distance, a frame-invariant quantity, one that all observers agree on, involving both the spatial separation between the wormhole mouths and the time offset between them. Call this product d times delta t. Hawking argued that the quantum gravity cutoff should occur when this invariant distance shrank to about the Planck length squared. And when you measured the distortion that way, the perturbation was not tiny. It was of order 1. Spacetime, by that reckoning, was being ripped apart, not gently nudged. The chronology horizon, Hawking concluded, would be destroyed. The time machine would never switch on. Kim and Thorne thanked Hawking, in the acknowledgements of their paper, for sending them a transcript of his argument, in which he contended that quantum gravity would not cut off the divergence until after it had already managed to prevent the formation of closed timelike curves. The disagreement was courteous, technical, and unresolved. Two surveyors, standing at the same cliff, measuring the height in two different ways, and arriving at opposite verdicts about whether the ground was safe. The physics, at this point, simply could not decide. Why does this matter? Because the question is not academic. If chronology protection holds, it tells us something profound about the structure of physical law. That causality is not merely a feature of our corner of spacetime, but a principle enforced universally, protected by the quantum vacuum itself. If it does not hold, if closed timelike curves conform, then the cosmos permits time travel to the past, and we are left to explain why we have never seen it, why no time travelers from the future have arrived, why Hawking's Party for Time Travelers, held at noon on June 28, 2009, in Cambridge, with invitations sent only after the event, drew no guests. Hawking sat there a long time, he said. No one came. He took it as experimental evidence, tongue-in-cheek, that the conjecture was right. But the absence of visitors is not a proof. It is a silence, and silence can mean many things. So what happens at a chronology horizon when you try to thread the needle between divergence and cutoff, between formation and destruction? To answer that, we need to look more carefully at the machinery, at the real, technical steps physicists take when they calculate what the vacuum does near a time machine. The first step is to specify the spacetime, its geometry, its causal structure, the shape of the time loop you are trying to build. For most calculations, this means a traversable wormhole. Two spherical mouths connected by a throat, threaded with exotic matter to hold it open. Exotic matter is matter with negative energy density, and it violates the weak energy condition, a classical rule that says energy density should never be negative as measured by any observer. Negative energy sounds impossible, but it is not. The Casimir effect provides it. Between those two metal plates, the vacuum energy density is negative, lower than the energy of empty space far away. The effect is real and measured. But scaling it up to wormhole size is another question. A wormhole with mouths a meter across would require exotic matter in quantities no one knows how to produce. Still, for the sake of the calculation, assume it exists.
One mouth stays here, the other is accelerated, taken on a round trip at relativistic speed, or lowered into a gravitational field, or simply left to sit while the cosmos expands around it. The goal is to make time pass at different rates for the two mouths, so that stepping through one delivers you into the past of the other. As the time offset grows, something begins to happen at the throat. A light ray emitted from one mouth, traveling through the wormhole to the other, and then through normal space back to the first, takes a certain amount of time. As the mouths desynchronize, that round-trip time shrinks. Eventually, it approaches zero. The moment it reaches zero, you have a closed null curve. The light ray, and anything traveling with it, returns to its own starting point in space-time. That moment is the formation of the chronology horizon. And it is at that moment, a hair's breadth before the curve closes, that the calculation of vacuum polarization begins. Vacuum polarization is the quantum field theoretic effect, where the presence of a curved or time-dependent background causes the vacuum state to carry energy and momentum. To compute it, you need to know the two-point function, a mathematical object that describes how quantum fluctuations at one point in spacetime are correlated with those at another. In flat, empty space, this function has a simple, well-behaved form called the Hadamard form. Near a chronology horizon, it does not. The trouble is that as you approach the horizon, pairs of points that are space-like separated, unable to influence each other in normal spacetime, become connected by closed loops. The distinction between past and future blurs. The two-point function, which depends on that distinction to be well-defined, begins to break down. When physicists renormalize the stress-energy tensor using this ill-behaved two-point function, they find divergences, infinities that cannot be absorbed into the definition of the vacuum. The vacuum, near the horizon, is not in a vacuum state anymore. It is polarized, charged with energy, and that energy grows without bound as you approach the moment of closure. In Kim and Thorne's analysis, this divergence appeared as a term proportional to 1 over the proper time remaining until an observer crossed the horizon. The closer you got, the larger the stress energy. But because the coefficient was small, suppressed by the large size of the wormhole compared to the Planck scale, the total distortion, even at a Planck length from the horizon, was only about 10 to the minus 35, negligible. Hawking's objection was subtle. He argued that the proper time to the horizon was not the right variable. The relevant quantity was the invariant interval, the space-time distance that all observers, regardless of their motion, would agree on. For a wormhole with mouths separated by a distance d and a time offset delta t between them, this interval goes like d times delta t. As the wormhole is about to become a time machine, delta t shrinks towards 0, and so does this interval. Hawking claimed the divergence should be cut off when d times delta t shrinks to about the Planck length, not when an observer's proper time does. Measured that way, the stress-energy perturbation is of order 1, not tiny, but catastrophic. Space-time, under this reckoning, is not gently perturbed, it is destroyed. The chronology horizon never forms. The wormhole, in the attempt to close the time loop, collapses, or the throat pinches off, or the exotic matter is expelled. The exact mechanism is unclear, but the end result is the same. The time machine does not switch on. This is Hawking's chronology protection, not a law that forbids the construction of a wormhole or the manipulation of one mouth, but a physical instability that triggers at the moment of truth. You can build the pieces, you can bring them to the brink, but the act of closing the loop summons its own undoing. Here is where it gets genuinely strange. The divergence is not caused by anything you put into the machine. It is not the exotic matter failing, or the walls of the wormhole giving way, or a power supply running out. It is the vacuum, empty space, reacting to the geometry. The vacuum is not passive. It is a dynamical entity, seething with quantum fluctuations that respond to the curvature and causal structure of spacetime. Near a forming time machine, those fluctuations amplify. They loop back on themselves, just like the light ray on the fountain. Each lap around the chronology horizon adds energy, and there is no damping, no friction, no mechanism to dissipate it. The process runs away. And because energy tells spacetime how to curve, the amplified vacuum energy feeds back into the geometry, further amplifying the fluctuations. It is a feedback loop with no stabilizer. Engineers would call it an unstable system, one where any small perturbation grows without bound. Physicists call it a divergence, and they treat it as a sign that the equations have reached their limit, that the approximations have broken down, or that the configuration being studied is forbidden by a deeper law. In this case, all three interpretations are on the table. The most careful and rigorous result came in 1997 from three mathematical physicists, Bernard K., Marek Radzikowski, and Robert Wald. They did not calculate the renormalized stress-energy tensor directly, because to do so you need the two-point function, and they proved that near certain kinds of chronology horizons, the two-point function cannot be of the Hadamard form. They considered what they called compactly generated Cauchy horizons, boundaries past which the usual rules of cause and effect break down, and where the breakdown arises from a compact region of spacetime. They showed that at certain points on such a horizon, the past terminal accumulation points, in the language of differential geometry, the two-point function is necessarily singular. Not just large, but ill-defined. And if the two-point function is ill-defined, then the renormalized stress-energy tensor is ill-defined. You cannot compute it. The Samasia-Einstein equations, which say that spacetime curvature equals 8 pi g times the quantum expectation value of the stress-energy tensor, cannot even be written down at those points. The theory breaks down. K., Radzikowski, and Wald did not claim this proved chronology protection in the sense Hawking meant. They claimed something subtler, that Samasia quantum field theory, the framework used for all these calculations, is fundamentally incapable of answering the question. The equations become ill-posed at exactly the moment you need them. Whether this breakdown enforces protection, whether it means time machines cannot form, or merely that our tools are too crude to say, is a matter of interpretation. If you insist that physical law must always give definite answers, then the breakdown is a kind of protection by fiat. The cosmos forbids the question by making the physics undecidable. If you believe a deeper theory will resolve it, then K., Radzikowski, and Wald's result is simply a marker showing where chemical gravity ends and quantum gravity begins. Other counterexamples followed. Lee-Sin Lee and J. Richard Gott in 1997 found spacetimes where the stress-energy tensor remained finite everywhere. Amos Ory in 2005 and 2007 constructed time machine models with a compact vacuum core that satisfied the weak, dominant, and strong energy conditions, violating none of the classical constraints that were supposed to forbid such things. In 1998, Michael Cassidy and Stephen Hawking himself published a paper conceding that back reaction does not necessarily prevent the formation of closed timelike curves. Hawking, in other words, acknowledged that his own conjecture was not a theorem. The calculations show that in many cases, probably most, the vacuum polarization diverges and the chronology horizon is destroyed. But there are loopholes, configurations where the divergence is avoided or suppressed, and the question of whether those configurations are physically realizable, whether they are stable, whether they survive scrutiny in a full quantum theory of gravity, remains open. Ory, at the end of his 2005 paper, wrote plainly, "Stability remains the main open question. The models exist on paper. Whether they could exist in reality, whether they would survive the quantum fluctuations and gravitational instabilities that a real cosmos would throw at them, is unknown." Why does this matter? Because the fate of chronology protection is not just a question about time machines. It is a question about the structure of physical law itself. Causality, the principle that causes precede their effects, that the past is fixed and the future open, is so woven into how we think about the cosmos that it is hard to imagine physics without it. And yet general relativity, our best theory of spacetime, does not enforce it. The equations are local. They tell you how spacetime curves in response to matter and energy right here, right now. But they say nothing about the global shape of time, about whether world lines somewhere far away might loop back on themselves. Chronology protection would be an additional principle, a constraint beyond relativity, something that emerges not from the geometry alone, but from the quantum nature of fields on that geometry. If it holds, it tells us that causality is not an assumption we make for convenience,
but a consequence of deeper law. Perhaps the same law that prevents singularities from being naked, that hides them behind event horizons, that keeps the cosmos, in Roger Penrose's phrase, clothed. Penrose called this the cosmic censorship hypothesis, that singularities, the places where the equations break down, are always hidden from view, shielded by horizons. Chronology protection is a cousin of that idea. It says that causal pathology, the places where time loops back, are likewise forbidden from forming in the observable cosmos. The laws of physics, whatever they turn out to be in full, keep causality safe. But if chronology protection does not hold, if closed timelike curves conform, then we face a different puzzle. Why have we never seen one? Why does the cosmos, which permits them in principle, seem never to build them in practice? One answer is anthropic. Perhaps time machines do form somewhere, but any region containing them is unsuitable for observers like us. And so we find ourselves in the regions where causality is intact. Another answer is historical. Perhaps the conditions needed to form a time machine, the exotic matter, the precise configuration, the enormous energies, are so rare that they have not yet occurred in the observable cosmos, or occurred only in the very early cosmos where we cannot see them.
A third answer is that the paradoxes are real, and they are resolved not by prevention but by self-consistency. This is Igor Novikov's proposal. He argued that if time travel is possible, then the cosmos permits only those events that are consistent with their own past. You cannot shoot your grandfather because if you try, something will stop you. Not a physical barrier, but the simple fact that any history in which you exist and travel back must also be a history in which your grandfather survives. The billiard ball paradox, worked out by Fernando Echeverria, Gunnar Klinkhammer and Kip Thorne in 1991, illustrated this. They imagined a ball fired into a wormhole on a trajectory that would, upon emerging in the past, collide with its earlier self and knock it off course, preventing the very collision. The paradox seems sharp, but they found solutions. Glancing blow trajectories where the ball nudges its earlier self just enough to send it into the wormhole on the right path, creating a self-consistent loop. Often there were multiple such solutions, sometimes infinitely many, all for the same initial launch. Determinism in the presence of closed timelike curves is replaced by a strange multiplicity of consistent histories. The cosmos does not pick one. It permits all of them, somehow, simultaneously. This is the part I find hard to stop thinking about. In normal space-time, you fire a ball, and the laws of physics tell you exactly where it will go. Determinism, one future. In a space-time with closed timelike curves, you fire the same ball, and the laws permit many futures, all consistent with their own past, and nothing in the equations picks one over the others. It is not randomness, it is not probability in the quantum sense. It is a kind of logical multiplicity, as if the cosmos is less a single story unfolding and more a space of stories that agree with themselves. Novikov insisted this was not a problem. Consistency, he argued, is enough. The cosmos need not forbid time travel, it need only forbid contradictions. And if you look at the physics that way, closed time-like curves are not paradoxes. They are simply regions where initial conditions do not uniquely determine outcomes, and that is strange but perhaps not fatal. David Deutsch, thinking along similar lines in the context of quantum mechanics, proposed that time travel might be consistent if you allowed quantum superpositions of different histories, each one internally consistent, coexisting. But these are ideas, not settled physics. They point toward possible resolutions, not proofs. Other approaches have tried to avoid the chronology protection question by arguing that the cosmos has defenses in depth. Matt Visser, in a 1992 paper, laid out what he called a defense in depth strategy. Even before you get to vacuum polarization and chronology horizons, you have to deal with the Casimir effect, which might disrupt the wormhole. And even if that does not, the wormhole might be unstable to other perturbations. And even if it survives all that, back reaction might destroy it. And even if back reaction fails, quantum gravity might impose some other cutoff. The cosmos, in this view, fights time machines at every stage, layer upon layer, so that even if one defense fails, another takes its place. But this argument by accumulation is not the same as a proof. It is a bet that nature is consistent, that causality matters, and that somewhere in the stack of quantum field theory, general relativity, and quantum gravity, there is a principle that makes time machines impossible. Hawking bet on back reaction. Kay, Radzikowski, and Wald bet on the breakdown of sinomial theory. Others bet on exotic matter being unavailable in the necessary quantities, or on wormholes being classically unstable, or on holography, the idea emerging from string theory and the ADS/CFT correspondence that the quantum state of a region of spacetime is encoded on its boundary, and that the consistency of the boundary theory forbids bulk pathologies like closed timelike curves. That last idea has gained traction. In 2003, physicists studying Gödel-like spacetimes in the context of string theory found that when closed timelike curves would form, the geometry develops a holographic screen, a boundary where the usual rules of gravity cease to apply, and the physics is instead described by a lower-dimensional quantum field theory. That boundary theory, crucially, is unitary. Probability is conserved, information is not lost, and the theory does not permit the kinds of violations that time travel would entail. The bulk spacetime behind the screen can in principle contain closed time-like curves, but they are hidden, walled off from the exterior by the holographic boundary. An observer outside cannot access them. In 2010, further work in ADS/CFT showed that closed time-like curves in the bulk appear precisely when the boundary conformal field theory violates a unitarity bound, a constraint that follows from the consistency of quantum mechanics. If the boundary theory is unitary, and it must be to make sense as a quantum theory, then the bulk cannot have closed time-like curves. Holography, in this view, enforces chronology protection not by destroying time machines at the moment of formation, but by forbidding them from existing in any region accessible to observers. The cosmos does not stop you from building a time machine. It hides the time machine behind a curtain you cannot pull back. These are hints, not answers. The full theory is not in hand. What we have, 30 years after Hawking's conjecture, is a patchwork of calculations, counterexamples, rigorous no-go theorems for semiclassical schizophrenia physics, and promising leads from holography and quantum gravity. And woven through all of it is an honest acknowledgement: we do not yet know. The question of whether the cosmos permits time machines is a question about physics at the edge of what we can currently calculate. It involves quantum fields on curved spacetime, a regime where we have methods but not full control. It involves the Planck-scale, where spacetime itself is thought to be quantum and our usual notions of geometry dissolve. It involves the global structure of causality, a feature that general relativity treats as free input, but that quantum consistency might constrain. And it involves, perhaps most fundamentally, the interplay between local and global, between the equations that govern a small patch of spacetime and the principles that govern the cosmos as a whole. We are good at the local. We have Einstein's equations, we have quantum field theory, we have techniques for computing stress-energy tensors and curvature. But the global principles, the ones that would tell us which spacetime geometries are physically allowed and which are merely mathematically possible, remain partly hidden. Chronology protection is one candidate for such a principle. Cosmic censorship is another. Holography might be a third. They are all, at some level, bets that the cosmos is kind, that it does not permit the pathologies the equations allow, that causality and predictability are protected, that the fabric of spacetime is more robust than its formal flexibility suggests. Recent work continues to probe the edges. In 2024 and 2025, physicists computed exact solutions for quantum fields inside rotating black holes, Kerr-Newman and dionic Kerr-Sen spacetimes, and found that the blue shift instability Hawking predicted does indeed occur at the inner horizon,
a Cauchy horizon inside the black hole where closed timelike curves could, in principle, form. The fields diverge, the energy density runs away, and the horizon is disrupted. This does not prove chronology protection for all cases, but it confirms that in these particular geometries, the runaway feedback is real and not an artifact of approximation. In another 2025 paper, researchers working in a modified theory of gravity, hologravity, which violates Lorentz invariance at high energies, found that when you spin a black hole fast enough to bring it near the formation of closed timelike curves, the theory responds by making a new singularity, a torus-shaped region of infinite curvature that walls off the would-be time machine region. The closed timelike curves still exist in the mathematics, but the singularity makes them unreachable, sealed behind a boundary that cannot be crossed. Protection again, though by a different mechanism, and in a theory that may not describe our cosmos. What these calculations share is a pattern. Bring a region of spacetime to the edge of causality violation, and something intervenes. The intervention is not always the same. Sometimes it is vacuum polarization running away. Sometimes it is the breakdown of the equations themselves. Sometimes it is a new singularity appearing, or a holographic screen forming, or the exotic matter required to thread the wormhole proving unavailable in the quantities needed. The cosmos, it seems, has many ways to say no. But none of them is airtight. None of them applies in every case. And that leaves the question open. Is chronology protection a law, or is it a tendency, a pattern we see in most but not all solutions? A hint that the final theory will forbid time machines, but a hint we cannot yet prove. Consider the energies involved. A traversable wormhole, even a small one, mouths a meter across, throat a few meters long, requires exotic matter threaded through it. The Casimir effect between two parallel plates separated by a distance a gives you a negative energy density of magnitude roughly h bar times c times pi squared divided by 720 times a to the fourth power. For plates a millimeter apart, that is a pressure of about 1/100th of a Pascal, measurable but tiny. To hold open a wormhole, you need that negative energy density not between two plates, but throughout a three-dimensional region, and you need it to be strong enough to counteract the throat's natural tendency to collapse under its own gravity. Scale that up to a wormhole big enough for a human, and the total amount of exotic matter required is enormous, many times the mass energy of the Sun, depending on the geometry. No one knows how to produce that. The Casimir effect gives you negative energy, yes, but in trace amounts confined to tiny gaps. Scaling it to macroscopic size is not a matter of building a bigger apparatus. It is a matter of fighting the fact that as you make the plates larger or the gap wider, the energy density drops rapidly, proportional to 1/a to the fourth. You would need plates the size of continents separated by micrometers, or some other configuration entirely, and even then it is not clear the total integrated energy would suffice. Some proposals involve quantum inequalities, constraints derived from the uncertainty principle that limit how much negative energy you can concentrate and for how long. These inequalities suggest that while negative energy is real, the cosmos places strict bounds on its use, bounds that might make a traversable wormhole impossible to construct, even in principle. Others point out that the Morris-Thorne wormhole, the traversable geometry Thorne and his students worked out, assumes the exotic matter is already in place and stable. It does not tell you how to make it, or whether making it would trigger other instabilities, the wormhole mouths repelling each other, or the throat pinching off, or quantum fluctuations tearing the structure apart before you could ever move one mouth to build the time machine. These are practical obstacles, not fundamental laws, but they stack up. The cosmos does not make it easy. And then there is the question of cosmic strings. In 1991, J. Richard Gott showed that if you take two infinitely long cosmic strings, hypothetical one-dimensional defects in spacetime, relics of symmetry-breaking phase transitions in the very early cosmos, and pass them by each other at relativistic speed, the spacetime between them can develop closed timelike curves. The geometry of each string individually is conical. Spacetime around a cosmic string has a deficit angle, a wedge missing, so that if you walk around the string you complete a circuit in less than 360 degrees. When two such strings pass, their deficit angles add up in a way that can tilt light cones and form time loops. Gödel's calculation was exact and classical. No exotic matter needed, no wormholes, just ordinary cosmic strings with tension obeying the weak energy condition. It looked, for a moment, like a loophole. But Hawking, in his 1992 paper, proved a theorem. If closed timelike curves form from a region that is compact, finite, bounded, then the spacetime must somewhere violate the averaged weak energy condition. Gödel's strings are infinite. They extend forever in both directions. If you tried to make them finite, cosmic string loops, say, or segments, the theorem says you would need exotic matter somewhere to close the causal loop. The cosmos, again, charges infinity as the price, or it demands exotic matter, or it forbids the construction outright. Hawking's theorem does not say which. It only says you cannot have a finite, local time machine made of ordinary matter. The door is not completely closed, but the conditions to walk through it are beyond anything we know how to engineer. Frank Tipler's cylinder, the infinitely long spinning column of matter, faces the same issue. Rotate it fast enough, a good fraction of the speed of light at its surface, and the frame dragging is so extreme that light cones tip over and closed, timelike curves appear outside the cylinder, in the surrounding spacetime. The effect is real in the sense that the mathematics is sound, but the cylinder must be infinitely long. A finite cylinder does not work, or rather, Hawking's theorem says that to make a finite rotating cylinder form closed timelike curves, you would need to add exotic matter. And there is another problem. The cylinder must rotate faster and faster as you make it shorter, and at some point the surface velocity would exceed the speed of light, which is forbidden. Or the matter would have to be compressed to such densities that it collapses into a black hole. The cosmos does not give you the infinite cylinder. It gives you finite objects, and finite objects obey constraints, energy conditions, stability conditions, the speed of light limit, that collectively seem to prevent the construction of a Tipler time machine. Seem to, but again, this is not a theorem. It is a patchwork of obstacles, each one formidable, together forming a wall that no one has found a way over. Picture the Roman ring again. You have not one wormhole, but many arranged in a chain. Each wormhole is small, its throat narrow, its mouths close together. No single wormhole is close to forming a closed timelike curve, but the chain as a whole is. A photon traveling through the first wormhole, then the second, then the third, and so on around the ring, and finally back through ordinary space to the first, that photon can complete a loop. As you adjust the relative positions or time offsets of the mouths, you can shrink the total round-trip time, bringing it closer and closer to zero. At some point, you cross the threshold, closed null curves form. And because no single wormhole is under stress, the vacuum polarization at each throat stays small. Visser calculated that you could make the total back reaction arbitrarily weak by making the ring long enough, by adding more wormholes to the chain. The divergence, if it occurs at all, occurs not at any individual throat, but at the global chronology horizon, a boundary that wraps around the entire configuration. And at that boundary, Visser argued, serializer gravity simply cannot be trusted. You are too close to the Planck-scale, too deep into the regime where space-time itself is quantum. He called the boundary inside which the calculation breaks down the reliability horizon. Outside it, the equations say closed timelike curves form. Inside it, the equations give no answer. This is not a proof of chronology protection. It is a proof that the question cannot be decided with current tools, which, depending on your outlook, is either a loophole for time machines or an admission that we are asking sample physics to do something it was never built to do. Matt Visser reflected on this in a 2002 review. He wrote that his own view had shifted markedly over the years. Early on, he had been hopeful that chronology protection could be proved from first principles within security quantum gravity. He had worked through the calculations, seen the divergences, and thought they pointed toward a universal prohibition. But the counterexamples, the Roman ring, the models where the stress energy stayed finite, convinced him otherwise. Semiclassical quantum gravity, he concluded, is fundamentally incapable of answering the question of whether the cosmos is chronology protected. The theory breaks down at exactly the moment you need it. That breakdown might mean the cosmos enforces protection by making the physics ill-defined. Or it might mean we are simply at the edge of what semical methods can see, and a full quantum theory of gravity will give a clear answer, yes or no, once we have it. We do not have it yet. String theory offers hints. Loop quantum gravity offers others. Neither is complete. And so the question remains suspended, waiting for the final theory. What would a full theory of quantum gravity have to explain? It would have to tell us what space-time is at the smallest scales. Is it a continuum, smooth and infinitely divisible all the way down? Or does it have a discrete structure, a granularity at the Planck scale, so that there is no such thing as a distance smaller than the Planck length, or a time interval shorter than the Planck time? If space-time is discrete, then the divergences that plague semiclassical calculations might be cut off naturally, not by hand, but by the structure of the theory itself. The runaway blue shift, the piling up of energy on the fountain, would hit a limit. There is only so much energy you can pack into a Planck-sized region before the notion of space-time as a background stops making sense. At that point, you are not talking about fields on space-time anymore. You are talking about the quantum state of space-time itself, a regime where geometry and matter are inseparable, where the Einstein equations no longer apply because space-time is not a thing you can write equations on. It is an emergent property of something deeper. String theory approaches this by replacing point particles with extended one-dimensional strings, and by embedding space-time in a higher dimensional structure where the extra dimensions are curled up small. The strings can vibrate in different modes, and those modes correspond to different particles: photons, gravitons, quarks. Space-time itself, in string theory, is not fundamental. It is an approximate description that emerges when you look at the collective behavior of strings at low energy. At high energy, near the Planck scale, the approximation breaks down. Strings can split and join, topology can change, and the usual notions of distance and time become fuzzy. In such a framework, a chronology horizon might not be a place where equations diverge, but a place where the background geometry dissolves, where the question, does a closed timelike curve form, stops being well posed because there is no classical spacetime left to form it in. The theory would not say the time machine is destroyed. It would say the concept of a time machine, defined in terms of classical world lines through classical spacetime, no longer applies. Loop quantum gravity takes a different route. It quantizes spacetime directly, building it out of discrete loops of gravitational field, and finds the area and volume are quantized. They come in discrete units, multiples of the Planck area and Planck volume. In this picture, spacetime is not a continuum but a network, a graph where nodes represent quanta of volume and edges represent quanta of area. The geometry is discrete, and so is the causal structure. A closed timelike curve in such a setting would be a loop in the causal network, a path through the nodes that returns to its starting point. Whether such loops can exist depends on the dynamics, on the rules that govern how the network evolves. The theory is not yet developed enough to give a clear answer, but the discreteness might impose constraints. If there is a minimum time interval, then the idea of a light ray completing infinitely many laps in zero time, the runaway blue shift, does not make sense. The runaway would be cut off, not by quantum field theory on a classical background, but by the discrete structure of time itself. Again, this is not a proof. It is a possibility, a hint that the final theory might enforce chronology protection not by destroying time machines, but by making the construction of a time machine incoherent in the language of quantum geometry. Holography offers yet another perspective. The holographic principle, born from the study of black hole entropy and formalized in the ADS/CFT correspondence, says that the quantum state of a region of spacetime is fully encoded in a theory living on the boundary of that region. The bulk, the interior, is not fundamental. It is a kind of hologram, a three-dimensional image reconstructed from two-dimensional data. In the ADS/CFT correspondence, a gravitational theory in anti-de Sitter space, a spacetime with negative cosmological constant, like a saddle-shaped cosmos, is exactly equivalent to a conformal field theory, a quantum field theory without gravity, living on the boundary. The boundary theory is a standard quantum theory, unitary, predictable, well-defined. The bulk theory includes gravity, black holes, and potentially time machines. If the bulk develops closed timelike curves, what happens in the boundary theory? The answer, from several studies, is that the boundary theory develops an inconsistency. It violates unitarity, or it violates causality, or it becomes ill-defined in some other way. But the boundary theory is supposed to be a consistent quantum theory. It cannot violate unitarity. So if the bulk would have closed timelike curves, the correspondence forbids it. The bulk geometry adjusts, or a new boundary appears, or the configuration simply cannot exist within the framework. This is chronology protection from a completely different angle, not from vacuum fluctuations or back reaction, but from the consistency of the quantum theory that describes the boundary. The cosmos does not destroy the time machine. It refuses to be a cosmos in which the time machine is definable. These approaches, string theory, loop quantum gravity, holography, are not yet complete, and they do not yet agree. They point in different directions, use different languages, make different assumptions, but they share a common thread. At the Planck scale, the regime where time machines would form or fail, space-time as we know it breaks down. The classical picture, the smooth fabric that Einstein's equations describe, is an approximation. It works beautifully at large scales, at low energies, in weak fields. But near a chronology horizon, none of those conditions hold. The curvature is strong, the quantum effects are large, the geometry is dynamical and uncertain. The approximation fails, and with it, the question itself transforms. You are no longer asking, does this classical spacetime contain closed time-like curves? You are asking, does the quantum state of the gravitational field permit a configuration we would interpret, in the classical limit, as closed time-like curves? And that is a question we do not yet have the tools to answer rigorously. We have strong intuitions. We have calculations that work in certain limits. We have theorems that say submodule physics breaks down. But we do not have the final theory. Here is what we do have. We have Gödel's cosmos, a mathematical proof that general relativity by itself does not forbid time travel. We have the Morris-Thorne wormhole, a demonstration that you can write down a geometry allowing backward causation if you are willing to thread it with exotic matter. We have the Kip Thorne and Hawking calculations, showing that vacuum polarization near a chronology horizon diverges in most models, though the interpretation of that divergence, whether it enforces protection or is cut off by quantum gravity, is disputed. We have the Radzikowski-Wald theorem, a rigorous proof that Semitian gravity becomes ill-defined at certain points on any compactly generated Cauchy horizon. We have counterexamples, the Roman ring, the Li-Shin-Li models, the Ori compact vacuum core solutions, where the stress energy stays finite and closed time-like curves appear to survive. We have holographic arguments suggesting that quantum consistency on the boundary forbids bulk pathologies. We have recent exact calculations inside rotating black holes,
confirming that the blue shift instability is real, not an artifact. We have modified theories of gravity where singularities form to wall off the would-be time machine regions. And we have Hawking's time traveller party, an empty room in Cambridge, and no visitors from the future. Taken together, this is not a proof. It is a body of evidence pointing, strongly but not conclusively, toward chronology protection. The cosmos seems to fight time machines. It fights them in many ways, at many levels. But it has not yet shown us the final law that forbids them, and until it does, the conjecture remains open. Why does any of this matter, beyond the question of whether you could visit yesterday? Because causality is the spine of how we do science. Every experiment, every prediction, every law we write down assumes that causes precede effects, that the past is fixed and the future undetermined, that you can repeat an experiment and get the same result because the initial conditions determine the outcome. If closed timelike curves exist, that structure fractures. The past is no longer fixed. It can be influenced by events in the future. Initial conditions do not determine outcomes. Multiple self-consistent histories can arise from the same starting point. Repeatability becomes ambiguous. Run the same experiment twice, and if a closed timelike curve threads through the lab, the two runs might interfere with each other in time, giving different results. Novikov's self-consistency principle tries to save determinism by saying only consistent histories occur, but consistency is not uniqueness. The billiard ball has infinitely many ways to nudge itself onto the right path. Which one happens? The principle does not say. It cannot say. The equations permit all of them. This is not quantum indeterminacy, where probabilities tell you what to expect. It is a deeper ambiguity, one where the framework of prediction itself is unclear. And that matters because science is, at its core, the enterprise of making predictions. If I do this, what will happen? If the answer is many things, all consistent, and the theory does not pick one, then science in the presence of closed timelike curves becomes something strange and new. Not impossible, but requiring a rethinking of what a physical law is. So perhaps chronology protection is not just about keeping the cosmos safe for historians, as Hawking joked. Perhaps it is about keeping the cosmos safe for physics, about preserving the structure that makes physical law possible. If closed timelike curves could form anywhere, anytime, from generic conditions, then causality would be a local accident, and the predictability we rely on would be fragile, subject to sudden breakdown if someone or something engineered a time loop. That fragility feels wrong. It feels like the cosmos should not work that way, but feeling is not proof. The cosmos does not care what feels right to us. It is what it is, and the only way to know what it permits is to calculate, to observe, to push the equations to their edges and see where they break. That is what Hawking did. That is what Kim and Thorne did, and Visser and Kay, Radzikowski and Wald, and everyone who has worked on this problem since. They pushed the equations to the edge, and the edge pushed back. The vacuum polarization diverged. The two-point function became singular. The simple Semel framework broke down. The bulk geometry conflicted with the boundary unitarity. Nature, it seems, does not make it easy to violate causality. Whether it makes it impossible is the question that remains. Consider one more analogy. You are holding a microphone. You bring it close to the speaker that carries its own output. At first, nothing happens. A bit closer, and you hear a faint hum, a low feedback tone. Closer still, and the hum grows louder, begins to oscillate, to howl. And then, if you bring the mic right up to the speaker, the feedback runs away. A scream that saturates the amplifier, distorts the signal, and either blows the speaker or trips a safety circuit that shuts the system down. The system will not let you complete the loop cleanly. It fights you with its own amplification, turning your attempt into its own destruction. That is what happens at a chronology horizon. The loop you are trying to close is the causal loop, the path through spacetime that would let an effect precede its cause. The amplifier is the vacuum, the quantum fields that live on spacetime. The feedback is the stress-energy tensor, growing without bound as the loop tightens. And the safety circuit, if there is one, is whatever principle, in the final theory, cuts off the divergence or makes the configuration impossible.
We do not know yet if that circuit exists. We do not know if the scream saturates at a finite level, allowing the loop to close, or if it trips the breaker and shuts the machine down. But every time we calculate, in every model where we have the tools to look, we find the feedback. We find the instability. We find the system fighting itself. One last human moment. In 1991, a physicist named Joseph Polchinski was thinking about time travel and paradoxes, and he sent a letter to Kip Thorne describing a thought experiment. Imagine you have a billiard ball and a wormhole. The wormhole's mouths are arranged so that if you shoot the ball through one mouth, it emerges from the other mouth in the past, in a position to collide with its earlier self and knock it off course. The setup is clean, classical, easy to visualize. Now fire the ball. If it goes into the wormhole, it comes back and hits itself, preventing it from going into the wormhole, a paradox. Thorne handed the problem to two graduate students, Fernando Echeverria and Gunnar Klinkhammer. They worked it out with the full machinery of general relativity and classical mechanics, and they found something surprising. There was no paradox. There were solutions, trajectories where the ball from the future glances off its past self at just the right angle to send the past self into the wormhole on exactly the path needed to produce that glancing blow. A self-consistent loop. Not only were there solutions, there were often many solutions, sometimes infinitely many, all perfectly consistent. The ball did not have to knock itself off course, it could nudge itself onto course. For certain initial conditions, the equations permitted a whole continuum of outcomes, all of them satisfying Newton's laws and the geometry of the wormhole, all of them free of contradiction. Echeverria and Klinkhammer published the result in 1991. Novikov, independently, arrived at a similar conclusion and called it the self-consistency principle. And Thorne and others started to take seriously the idea that time travel, if it were possible, would not break physics. It would simply constrain it, forcing only those events that agree with their own past. The principle feels almost tautological. What happens must be consistent with what happened. But in the presence of closed timelike curves, that tautology has teeth. It rules out certain trajectories, allows others, and in cases where many are allowed, it leaves the outcome undetermined in a very strange way. This is worth sitting with for a moment. We are used to determinism and we are used to randomness. Determinism says the initial state fixes the future. Randomness, quantum or classical, says the future is probabilistic, a weighted sum over possibilities. But Novikov consistency is neither. It is a constraint without probabilities. The cosmos does not pick a history at random from the allowed set. It does not evolve one initial state into one final state. It exists in whatever configuration is self-consistent, and if many configurations fit, the theory does not tell you which one you are in. Some physicists find this beautiful, a kind of logical completeness where the cosmos is its own explanation, requiring nothing but self-agreement. Others find it unsettling, a breakdown of the predictive power that makes physics useful. Both reactions are reasonable. The mathematics is clear. Self-consistent solutions exist, often in abundance. The interpretation, what it means for physics as a framework, is not. David Deutsch took the idea further. He asked what happens if you add quantum mechanics to the mix. In quantum mechanics, a particle does not have a single trajectory. It exists in a superposition of many trajectories, and you only get a definite outcome when you measure. Deutsch proposed that near a closed timelike curve, the quantum state evolves into a superposition of all the self-consistent histories, each weighted by its quantum amplitude. You do not get one billiard ball trajectory, you get a superposition of all the glancing blows, all the consistent loops, interfering with each other quantum mechanically. When you measure the outcome, you collapse the wave function and see one history, but the structure underneath is a sum over consistent loops. This is mathematically elegant, and it removes some of the conceptual sting of non-uniqueness. Quantum mechanics already has superposition and probability built in,
so adding time loops just constrains which terms appear in the sum. But it also introduces new puzzles. The probabilities do not always come out normalized. Sometimes the sum over consistent histories gives amplitudes that do not add to 1, violating the basic rules of quantum mechanics. Deutsch argued this could be fixed by interpreting the results carefully, by thinking of the closed timelike curve region as a kind of measurement apparatus that post-selects certain outcomes. Others argued it pointed to an inconsistency, a sign that quantum mechanics and closed timelike curves are incompatible. The debate is ongoing. The machinery works after a fashion in toy models. Whether it works in realistic spacetimes and whether it preserves everything we need from quantum mechanics is unknown. And so we arrive back at the chronology horizon, the place where all these threads converge. It is the boundary between the region where time has a direction and the region where it loops. It is the moment when the first light ray completes a circuit, when vacuum fluctuations begin to amplify, when the two-point function stops being Hadamard, when semiclassical gravity ceases to give answers. It is the edge of what we can calculate and the beginning of what we need quantum gravity to resolve. It is the place where, if chronology protection holds, the cosmos steps in and stops the process. And if protection does not hold, it is the place where causality becomes negotiable, where the past opens up and the future reaches back, and the structure we call time becomes something we do not yet have words for. We do not know which side of that divide we live on. We do not know if the cosmos permits closed time-like curves or forbids them, if the chronology protection agency is real or a hope. What we know is that the question is not settled, that the calculations we can do give mixed answers, and that the final answer waits in the theory we have not yet written. The numbers themselves tell part of the story. A Planck length is unimaginably small, 1.6 times 10 to the minus 35 meters, a billion times smaller than a proton, a scale where the notion of distance starts to lose meaning. A Planck time is correspondingly brief, about 5 times 10 to the minus 44 seconds, the time it would take light to cross a Planck length. These are not merely small numbers, they are the scales at which the quantum uncertainty in the position of a particle becomes comparable to its Schwarzschild radius, the size of the black hole that particle would form if compressed. Below these scales, the distinction between matter and geometry dissolves. Spacetime, as a smooth background, ceases to be a useful concept, and it is at these scales that the chronology protection question is decided. Kim and Thorne argued that when you are 1 Planck length from the chronology horizon, the metric distortion is only about 10 to the minus 35, negligible. Hawking argued that the right measure gives a distortion of order 1, catastrophic. The difference between those two conclusions is not a matter of arithmetic, but of physical interpretation. Which distance do you measure? Which frame do you trust? What counts as the cutoff? The equations themselves do not decide. They give you both answers depending on how you ask. And so the debate, in the end, is not just about vacuum polarization or stress energy tensors. It is about the right way to think about spacetime near its own edge, about what quantum gravity will say when we finally have it. Hawking never proved his conjecture. He knew that. In 1998, 6 years after publishing the original paper, he co-authored another with Michael Cassidy, examining a different class of spacetimes. They found models where the renormalized stress-energy tensor did not diverge, where the back reaction stayed finite, and where closed time-like curves appeared to form without obstruction. Hawking, in the abstract, conceded that the results did not support a universal prohibition. Back reaction, he wrote, does not necessarily prevent the formation of closed time-like curves. The conjecture might still be true, he suggested, for reasons beyond mathemata, perhaps in the full quantum theory. But the mechanism he had identified, the diverging vacuum polarization, was not airtight. This is how science works. You propose an idea, you calculate. You find where the idea holds and where it breaks. You revise. Hawking revised. He did not abandon the conjecture, he still thought it was probably true, but he acknowledged the limits of what he could prove.
That honesty is worth more than any neat conclusion. Amos Ory, working in the 2000s, pushed those limits further. He constructed spacetimes with a compact region, a torus of empty space surrounded by a shell of rotating matter, or, in another model, a torus of vacuum surrounded by ordinary dust, where closed timelike curves formed inside the torus, and the stress-energy tensor satisfied all the classical energy conditions. No exotic matter, no violations of the weak or dominant or strong energy condition. Just ordinary matter, arranged in a precise and carefully tuned configuration, and the geometry it produces includes time loops. Ory's models are not realistic in the sense that no one knows how to assemble such a configuration, and he himself noted that stability remains the main open question. A configuration can satisfy the energy conditions and still be unstable, perturb it slightly, and it might collapse, or radiate away its energy, or develop a singularity. But the models exist as solutions to Einstein's equations, and they show that the obstacle to time machines is not, in these cases, a violation of classical energy bounds. The obstacle, if there is one, is dynamical. It is a question of whether such configurations can form, whether they can survive, whether the cosmos allows them in practice even though the equations allow them in principle. That question, again, is beyond what we can currently answer. We can write down the geometry, we can check the energy conditions, we can compute the curvature. We cannot yet say whether the configuration would survive the quantum fluctuations, the gravitational waves, the perturbations that a real cosmos would throw at it. For that, we would need to evolve the full Einstein equations, coupled to quantum fields, in a regime where both are strongly dynamical. We do not have that capability yet. So where does that leave us? 33 years after Hawking wrote that there seems to be a chronology protection agency at work, the evidence is this. General relativity alone permits time machines. Many exact solutions contain closed timelike curves, and nothing in the classical field equations forbids them. Quantum field theory in curved spacetime, applied to those solutions, almost always finds that the vacuum stress energy diverges at the chronology horizon, and that divergence, if taken at face value, would destroy the horizon and prevent the time machine from forming. But the divergence occurs at the edge of where semicolon methods are reliable, and reinterpreting it in terms of quantum gravity gives ambiguous results. Small distortions in one measure, large in another. Rigorous mathematical results, like Radzikowski Wald, show that serialization gravity breaks down at exactly the points where we need it, rendering the question unanswerable within that framework. Counterexamples exist where the divergence is avoided or where closed timelike curves form without violating energy conditions, though the stability of those models is unproven. Holographic approaches suggest that quantum consistency forbids bulk time machines, but those approaches are not yet general enough to cover all cases. Recent exact calculations confirm that in certain black hole interiors, the blue shift instability is real and severe. Modified theories of gravity find new singularities that wall off the time machine regions. And experimentally, we have the silence. No visitors from the future, no detected closed timelike curves, no sign that time travel has ever occurred or is occurring. That silence is not proof, but it is data. The cosmos, it seems, does everything it can to stop you from building a time machine without proving that the construction is impossible. It hides the loopholes behind infinities, Tipler's infinite cylinder, Gott's infinite strings. It charges exotic matter as the entrance fee and makes exotic matter difficult to produce in useful quantities. It triggers instabilities at the chronology horizon in most models. It makes the equations break down where they need to give answers. It wraps the problem in enough layers of difficulty that no one has yet found a clear path through. And yet, the path is not conclusively blocked. The conjecture remains a conjecture. The final law, if there is one, is not in hand. What we have is a pattern, a weight of evidence, and the honest edge of what we can say. The cosmos destroys time machines the moment you turn them on. That is what the calculations say, in most models, most of the time. The vacuum roars to life, the energy diverges, the chronology horizon is ripped apart before the first time loop closes. But physics does not say it must. Not yet, not with the force of a proven theorem. It says it probably does, that the conditions for survival are narrow and perhaps unphysical, that every route we have tried runs into a wall or a cutoff or an ambiguity that forces us to stop. It says we are at the edge, looking at a question that superclass physics cannot answer and quantum gravity has not yet resolved. It says the door is not open, but it has not been proven locked. And that is the honest place to stand. Not in certainty, not in speculation, but in the acknowledgement that the question is live, that the cosmos is teaching us something about causality and time and the limits of what it allows, and that the final lesson is not yet clear. Stay curious.